very, very nice to be here, and thanks to James for setting us up. Thanks everyone for coming. I've had lots of little discussions about rigor with people over the years, and I always thought it was kind of amazing that there's not a huge literature on mathematical rigor in physics, because it seems like such an important topic. So I kind of jotted down some of my thoughts about that. It's obviously nice to have some examples, and I've been working on foundations of canonical quantum gravity for a long time now, and one of the things that's famous in this approach to quantum gravity is how incredibly unrigorous a particular equation called the Wheeler-DeWitt equation. And I can't remember who did it first, but the idea is that the whole equation is so badly defined that you always have to put it in inverted commas whenever you write it down. So that's what I've done here. And so I actually had some really productive chats with Rami, who's here, about rigor in particular, so some of this is inspired by him. The actual historical work, it's nice to know some historians who can go to archives and do things like that, has really been done by Alex Blue and Dean Rickles, and so I'll use some of the sources that they found a little bit later. I also just wanted to plug the Philosophy of Physics Society. If none of you, it's free for students, extremely reasonably priced. I think it's €20 or something or less for everyone else. Have a look on the website. Please do join if you're interested. It supports the Journal of Philosophy of Physics as well, which is an ideal place to publish stuff on rigor in physics. So what I'm going to do is talk a little bit about the general question of rigor in physics, come up with a proposal that we might think that there's another notion of rigor which I've now learned is called middle-brow rigor, but which I'm going to call physicist rigor. And then I'll kind of talk briefly about the constraint quantization program, really designed principally by Dirac, but others contributed a lot, and then the particular application of that to relativity in contexts of work done by DeWitt in the mid-60s, and how we can think about particularly the credit and the stabilization of the formula of the equation that DeWitt had as really embodying a kind of role of physicist rigor, which is clearly in this case different from mathematician's rigor. So I found this nice quote in a recent paper by Weatherall and Wolfson about a kind of standard view of rigor. I'm really not a philosopher of maths, but this seems quite sensible to me. Mathematical proof is the primary form of justification of mathematical knowledge, but in order to count as a proper, a rigorous mathematical proof, and thereby to function as justification for a piece of mathematical knowledge, mathematical proof must be rigorous. Mathematical proof is rigorous if and only if it can be routinely translated into a formal proof. And the extent to which that's a unitary thing and predeterminate in space and time perhaps seems to me like something that might be underdetermined, but at least I've got a kind of intuition for what that notion of rigor means. And one may think that the kind of role of rigor in physics is really about the lack of it. In particular, in these sources that Rami pointed me towards, there's an idea that what physicists are doing is somehow a kind of a rushed or heuristic or theoretical version of mathematical proof. They're not rigorous. They're kind of indicative. And so really, when we have a proof in maths or physics, in physics, it's indication often that there is a kind of genuine mathematical proof out there, and so there's then a kind of project for later generations of physicists and mathematicians to kind of rigorize a derivation in physics. So I like that Alex Bloom and James. You actually changed the terminology. You initially called it repairing, which I quite like, but then the later version, I think you call it cleaning up proofs. But I think this is the kind of idea that there's a kind of fixing job, that you have this proof, it's got some kind of infelicities, problems with mathematics, and it gets kind of fixed up so that it eventually becomes rigorous in the sense of the standard view. And it seems this idea you find continuous. I couldn't resist giving a talk in Paris to give a quote about Poincaré. and this is from Thébault on examining his thesis in 1878. At first glance, it seemed clear to me that Poincaré's thesis was out of the ordinary and fully deserved to be accepted. Certainly it contained enough results to furnish material for several good theses. But it must be said without hesitation, if an accurate idea is to be gained of the way in which Poincaré worked, that many points required corrections and explanation. Poincaré was an intuitive mathematician. Once at the summit, he never retraced his steps. He was content to have broken through the difficulties and left it for others to trouble themselves with mapping out the royal roads that would lead more easily to the goal. He willingly did the corrections and tidying up what seemed necessary, but when asked him to do so, he explained to me that he had many other ideas in his head and he was already occupied with some of the great problems or solutions he'd given us. So the idea is that even in mathematics, someone is great as Poincaré. Sometimes they just rush through things and that's their role, and other people can tidy it up. And so it's quite similar the way that Poincaré is working and other mathematicians are kind of working with him to go back after and clean up his proofs, to the way that physicists and mathematicians kind of work together. And so the idea is that we have this notion of an intuitive mathematician who kind of guesses the way to a result, doesn't follow the rigorous standards of mathematics, but there's an indication that there is a proof that does follow the rigorous standard of mathematics, kind of hiding behind it, and that's what the concept of rigor does for us in physics. It's just this kind of this norm, and often what physicists are doing is kind of doing something that can be later turned into a rigorous proof. And there seems to be something a bit kind of magical about it, that how does Poincaré kind of manage to do something that just has just the right features? He has this kind of great intuition that gets him to the right result whilst missing out a few steps, but it's such that it can always be kind of cleaned up and rigorized later. So I thought we'd just have a definition of something of this kind of process. I'll call it rigorous magic. So it's just a kind of derivation that leads to formal expressions that aren't really well defined, but they're kind of later formally processifiable. They can be translated into unambiguous expressions with well-defined mathematical objects, or into derivations that can be translated into proofs in the mathematical sense. It really should be called, I guess, rigorizable magic, but that sounded a bit silly, so I stuck with rigorous magic. And the two examples, I think we've already kind of mentioned them implicitly already, that are famous from physics of kind of object in particular. I'm really going to focus on objects being well defined rather than derivations being kind of turned into proofs, because that will be useful for what we talk about later. The Dirac delta function, which Dirac kind of, I think without there are historical precedents, that he kind of intuited this particular object, which is famously not a function, but was formally processifiable in terms of the theory of distributions later. And then the Feynman path integral, which really was kind of pathologically, particularly in terms of the measure, which again will be kind of relevant for what we talk about a bit later, not a well-defined object, ill-defined, but as kind of time's worn on, to a reasonable degree of rigor, you can now write things that are kind of a cleaned up version of a Feynman path integral, and start kind of using them as according to Lisa's standard of a fairly kind of rigorous theoretical physicist. And so one of the questions that one might want to ask is, well, how do we explain this phenomenon? What's going on? And there seems to be two obvious ways to explain the existence of rigorous magic. One is this intuition idea that Dirac and Feynman, like Poincaré, they can just kind of see this derivation or this object and intuit that it's going to be mathematically kind of processifiable, and later we find out that it is, and it's just kind of I mean, maybe you'd have to give some kind of Platonistic explanation of what's going on, I don't know. Another kind of probably more plausible explanation of what's going on is that lots of the time it isn't rigorizable, and we just don't remember those examples, and we just have a kind of confirmation bias that we're just like, well, it's amazing. These guys, they can come up with these sloppy mathematics that turns out really well, and we just forget about the bits where it didn't work out. But I actually don't think this is even the right question. because it kind of makes everything, makes our interpretation of theoretical physics practice so dependent upon what happens later. So it's kind of like a promissory note. Is it something that can be made rigorous later, according to science and mathematics, or not? And then we try and interpret what's going on. But actually, at least what I'm interested in is not how a mathematician thinks about physics done 20 years ago. It's how physicists think in their own kind of milieu, in their own period. What do they, or how do they understand the kind of concepts of rigor? And moreover, like, if you talk to theoretical physicists, what they care about is not really whether a mathematician is going to be happy with what they do. They're not, to a large extent, even worried about whether mathematicians think what they're doing is rigorous. That just isn't important to them, in that, at least in the kind of fully rigorous kind of mathematical sense. Maybe not all physicists, but many physicists. It just isn't a motivation for them. But on the other hand, it's clear that they're not like anything goes. You can write down any expression you want, and we have no norms of rigor at all. And so I think the obvious move is to think about being constructive and come up with a different notion of rigor, which is something that isn't completely permissive, but is less restrictive than the mathematician's notion of rigor. And my proposal is that this isn't going to be a unitary thing. There isn't one notion of rigor for theoretical physics. It's going to be quite kind of local within particular communities. I'm going to talk in particular about community working in quantum gravity in a particular time period, really the late 50s and 60s and early 70s, I guess. And so it's a norm about mathematical practice, legitimate derivations and formal objects that's kind of situated in a time and place, in a kind of network of community of people who interact and work with each other, and it's subject to change. What I claim is that this is a kind of useful concept in history and philosophy of physics, because it allows us to actually understand the process by which a particular equation was accepted as kind of well posed and why credit was given in a particular way. So in order for me to do that, I'm just going to give an extremely quick, and I kind of had a much longer talk that I had to cut down over the last few days, idea of what this program is even about. And I've managed to find two little diagrams that will hopefully help. So the first idea is really just staying in the realm of classical physics. So classical physical theories have a canonical formulation, a Hamiltonian formulation. Those are kind of the class of theories which have unconstrained phase spaces, have a nice kind of, the Euler-Lagrange equations are kind of well posed in a kind of important sense, and those are the kind of standard theories that have a well-defined Poisson bracket structure, and you can use that to kind of build a quantum theory, and that's the kind of base camp for most approaches to building a quantum theory rigorously. But there is a whole class of theories in which the Euler-Lagrange equations are not kind of inherently well posed, and this manifests itself as the failure of invertibility of the Legendre transform. But the long and short of it is you end up with constraints on the phase space. And other people worked on it. Dirac was the first person to really isolate these theories, and they're essentially gauge theories. So there's a formalism for doing gauge theories in classical gauge theories in Hamiltonian mechanics called constrained Hamiltonian mechanics. And there's a classical way of fixing this problem, which is to identify within the surface defined by these constraints kind of directions of degeneracy, which are actually generated by the constraints themselves, to project out these directions and then build a phase space which has kind of well-posed equations of motion. And this is the kind of theory of symplectic reduction. Lovely, geometric, beautiful, practice extremely difficult to do, particularly with complicated theory like general relativity. And so what Dirac suggested is that we can adopt an approach where we do a quantum analogue of that reduction procedure, a quantum analogue of projecting out the degeneracy. So the kind of royal road to building a quantum theory out of a constrained phase-space theory would be to apply this geometric reduction. You end up then with a kind of phase space that has the right structure, it's unconstrained. Poisson bracket gives you kind of unique dynamics, and then you just apply a standard quantization procedure there. But what Dirac kind of intuited or kind of hypothesized was that one could apply the canonical quantization procedure just to the phase space, bring the constraints along with you into some kind of auxiliary or kind of first level quantum theory, and then impose the constraints as some kind of analog to the classical reduction to build a quantum theory. And so this is the Dirac kind of constraint quantization program that he kind of most kind of clearly articulated in a book from 1964, but was kind of designed really in the late 50s. And like I said, other people contributed. And I think very early on it was understood that there was various problems of rigor in this approach. First, that the constraint functions. I'll describe the approach first, then talk about problems of rigor. So the idea really is you apply the constraint functions as operators annihilating the wave function, and then you build the physical states out of solving this equation. And then you just assume that you have self-adjoint operators defined on the physical Hilbert space that you can then use as your algebra of observables. And that will then give you this kind of quantum theory that's equivalent to what you would have got if you'd gone via this other kind of, in some sense, mathematically cleaner route, which is quite difficult to implement in practice. But there are all these kind of ambiguities of definition in this approach. There's factor ordering ambiguities that you find in the definition of the constraint, which is a particular problem of general relativity, because you have kind of terms that involve P's and Q's, and it's ambiguous which way of ordering the operators. The constraint operator itself is generally not self-adjoint, particularly when your functional space is going to be have boundaries or certainly not kind of be in the realm of the theorems that give you self-adjointness. Problems of finding dense domains for the constraint operators. And the final problem is one that I'll talk a bit about, is the problem of actually defining an inner product. Because in some sense, if your story is that you're building a Hilbert space by definition has to have an inner product, but this procedure doesn't guarantee you that you have such an inner product. So in some sense, you're not really defining a Hilbert space, you're defining something that you hope is a Hilbert space. However, what was done subsequently over many decades in various approaches, one that I'm most familiar with is refined algebraic quantization. Closely related approach is BRST quantization. Is that so long as the gauge symmetries are fairly simple, we can usually find a way to fix these problems, and for a large class of physical theories, we get this kind of rigorous magic kind of type scenario in which something was done kind of sloppily by Dirac, it's often by Dirac, and someone was later able to kind of clean it up and make it rigorous, at least to the standards of pretty serious theoretical physics, if not pure mathematics. What I'm going to talk about is a case in which things didn't quite work out this way. Did I get my water actually? How am I doing for time?
You've got 12 minutes until 1:45, but you've got more time than that if necessary.
So, Dirac was a physicist. He was interested in creating new theories, really, and it quite remarkably contributed not just to quantum mechanics and relativistic quantum mechanics, but to general relativity itself. So that the Hamiltonian formulation of general relativity, again, various other people worked on it, but the kind of precise formulation of general relativity as a constrained Hamiltonian theory it was kind of presented by Dirac in a paper in 1958. Very shortly later, Arnowitz, Dieser and Miesner cleaned it up and put it in a slightly different formalism, and so it's often called the ADM formulation, but it's really the Dirac formulation of general relativity. And the reason he was doing this is because he wanted to quantize it. So he was inventing both a constrained Hamiltonian approach to general relativity and a general methodology for quantizing constrained Hamiltonian theories, because he wanted to build a theory of quantum gravity. At the very point in which he got to the situation where he had the tools, he decided the entire project was doomed and ill-defined and gave it up. So he didn't really pursue it after the late 50s, early 60s. And one of the kind of immediate conceptual problems, which I spend a lot of my time thinking about, that you find in this approach is that the Hamiltonian itself, in general relativity and other theories with a particular type of gauge symmetry, is one of the constraints. And so when you apply the Dirac constraint quantization procedure, just naively without really worrying about everything being well defined, the immediate consequence is that the Hamiltonian, or the states that you use to build your physical Hilbert space, will satisfy an equation in which the Hamiltonian itself annihilates them, which essentially means that you're enforcing time independence as a gauge condition. And I've got various problems with this that I won't talk about the motivation. What I really want to do is talk about the nature of that equation. This kind of heuristic idea of just writing Hamiltonian of general relativity, where you put hats on things, some wave function over three geometries equals 0, really goes back. It's in a sense obvious once you have a constrained Hamiltonian formulation of general relativity in which the Hamiltonian is a constraint, and the Dirac constraint quantization procedure, which tells you that to do the quantum version of reduction, you promote the constraints to operators and kind of hit the wave function with them. And this, like I said, this equation was known to various people, Dirac himself, Bergman, Anderson, the Syracuse school in quantum gravity, already by the late 50s and certainly by the early 60s, and it appears in these various kind of sketchy forms. But the equation that people think about when they think about this formalism is really not that written down by Dirac or Bergman. It's a form of the equation written down by Bryce DeWitt in 1967, and published in a paper in 1967, and kind of discussed by him in I think unpublished work from really the mid-60s. And various talks John Wheeler gave, he kind of discussed the equation in this form as well. And so it's called the Wheeler-DeWitt equation. And as we'll see, the kind of attribution of credit for this equation is disputed by Bergman most kind of pointedly, and by the end of the kind of I think even by the early 70s, certainly by the 80s, DeWitt himself had also moved away from the equation and kind of rejected it, saying it's a damned equation and should be confined to the dustbin of history. The kind of most important point to emphasize is that it's not an example of rigorous magic. This is not what happened, right? So I'm going to talk about the rigorization of the equation by DeWitt, and that being salient for him getting credit and for the process of the equation stabilizing as the Wheeler-DeWitt equation. But it's not the case that later on physicists or mathematicians could make it rigorous in anything close to a kind of substantive sense. Even certainly by the standards of modern theoretical physics, I think at least from the 80s onwards, certainly now it's just a completely ill-defined equation. And even in 1967, it was well understood that there were issues with it. Plausibly, it's just not formally precisifiable. There is just no rigorous version of the Wheeler-DeWitt equation. It's just a kind of damned equation that will sit forever in the kind of ill-defined territory. So what was so special? What did DeWitt do in 1967 to get to the heuristic forms were written down earlier? He wrote a particular form down in 1967. What feature of that equation was it that it kind of gained? There's no empirical evidence that this is the right equation. It's not a tested equation, which would be a different explanation for why he kind of got credit and why it was important. What was it that he did that was so special? And it's very obvious if you look at the actual form of the equation that isn't anything special at all. So the Hamilton-Jacobi formulation of general relativity was first kind of developed by Higgs and Perez. It's the same Higgs actually as the Higgs boson. How he transitioned from general relativity to particle physics, I don't know. So really, Higgs wrote down a kind of a first form that dealt with a particular type of constraint in the theory, the momentum constraint. And then Perez showed how to write down a kind of full Hamilton-Jacobi formulation in 1962. And those of you kind of familiar with Hamilton-Jacobi theory and Schrödinger's approach to quantum mechanics will know that Schrödinger essentially guessed that one could take the Hamilton-Jacobi theory and kind of use a particular ansatz. We take the principal functional to kind of go to the wave function to derive the Schrödinger equation. And if you know a little bit of physics, it's very, very obvious in the sense that if someone's written down a Hamilton-Jacobi equation of this form, that you can just move to a quantum version of it of this form, which is essentially just treating the wave function like the principal functional, and kind of the structural form of the equation is kind of very, very simple to be able to write down once you've got the Hamilton-Jacobi formulation. And so it's kind of obvious that this can't be what DeWitt got credit for, because this form of the equation would have been known to many, many people many years earlier. I probably can't read this, I'll just read out a little bit. So this is a letter found by Don Salisbury, I think, in the Bergman archives, if I got this right. So it's from Bergman to Wheeler, and Wheeler's supporting DeWitt and kind of pushing his program, and Bergman basically says, well, look, I hear that you've been calling this equation the DeWitt equation, but as I understand, I proposed a form of this equation in the 50s, it was known by various other people, and really it's just Perez is the one who kind of wrote this down from the Hamilton-Jacobi formulation, and he's very polite, but he's clearly quite upset. He's like, why are you going around telling everyone that DeWitt's done this amazing thing and quantized gravity when this is stuff that we did a long time ago? And I'm not sure, I think we got Dean or Alex to read Wheeler's handwriting, which I can't, and we can work out what this note said, but I'm not sure if I remember. And so what was interesting to me was to actually think about, well, what did DeWitt and Wheeler say about the origin of the equation? And so the obvious thing to do is to look at their interviews and their kind of memoirs. And so DeWitt, with his wife, wrote a kind of there's a joint interview, and that's republished in a book that's edited by his wife about his life. And he tells the story, and this is actually the most famous story that you find printed a lot as the origin story. It's quite a cool story. And so John Wheeler's basically, it's in the early 60s, DeWitt's in Northern Carolina in Chapel Hill, and Wheeler's his supervisor, remember, he's kind of very powerful, influential guy. He phones DeWitt up and he says, look, I'm changing planes in the airport near you. You should come to the airport and have a coffee with me. So DeWitt drives to the airport and they have a coffee, and Wheeler's basically bugging everyone about how to define an equation of quantum gravity. And then DeWitt says, well, I've read Perez's paper. It's not very hard, as we just discussed, to go from Perez's paper to the Wheeler-DeWitt equation. But he also, this is the salient point that we'll talk about later, he also writes down an inner product for the states. And then Wheeler got tremendously excited at this, whether this, it's not clear if it refers to the Schrödinger equation, the Wheeler-DeWitt equation, or the inner product, and began to talk about it all the time. He wrote a paper in it in 1967. His heart was, this is quite a lot later recollection where the equation has kind of been rejected by him. His heart isn't really in it, and he doesn't really know why everyone cared about it. So there you go. And probably more helpful is to look at some evidence from that time, and this is DeWitt's report on his own work, writing about himself in the third person to a grant agency that Don Salisbury found as well. And he talks about his progress, and he talks about the functional integral expression for the inner products, and that he's going to publish the work soon. So he's certainly already got the kind of elements of this in 64. The date of the meeting in recollection is a little bit confusing because this would be quite early, particularly given Perez's paper is only published in 62. So then Wheeler, right? So Wheeler, of course, did 20 interviews for the American Institute of Physics, and they're all online, so you can kind of search them. It's quite a useful resource. And in his recollection, he doesn't mention DeWitt at all. He said, well, he of course mentions Perez, and we found out that Perez definitely visited Wheeler at Princeton in the early 60s anyway, so he would have known about the Perez equation. Already, contra what DeWitt says, he can't have told Wheeler about the Perez equation, because it would have been Perez wrote the paper in which he derived the Hamilton-Jacobi equation essentially whilst visiting Wheeler, and thanks Wheeler in the paper. So it's very unlikely that that's what Wheeler got from DeWitt. And what Wheeler says, he doesn't mention the inner product at all, and he just says, well, actually it was Bargmann who helped me clear it up, and it should really be called the Bargmann-Wheeler equation. And so, I mean, he doesn't give much credit to DeWitt at this point. So what I was thinking, Alex, Dean and I were kind of trying to work out what on earth was going on. And so my kind of hypothesis was that really what must have been interesting to Wheeler at the airport was the inner product, not the form of the equation. And DeWitt, he had a specific response he explains in the 1967 paper to use the form of the Klein-Gordon inner product, basically built from the kind of current that you get in the Klein-Gordon equation, to produce an expression for the inner product, or for at least a kind of formula that allows you to calculate a quantity based upon that's related to the orthogonality of the states. Even if it's not strictly an inner product, it forms some of the functional, mathematical and physical roles that an inner product usually plays in quantum theory. And as I said, exactly, this is one example of the phenomenon of the equation not being well defined. There isn't a well-defined Wheeler-DeWitt inner product in the strict sense of it actually having a measure and being regularizable and positive. And so it's not really an inner product. It's in some sense a kind of less rigorous heuristic thing that has some of the functional role of an inner product.
You've been going for
Okay, great. I've got 2 more slides. And so Alex went to the Wheeler archives and found the notebook of that day. And I don't think this has been kind of published at all by anyone as yet. And so he found the notes, the meeting, and exactly what we were kind of intuiting, that Wheeler didn't write down the Wheeler-DeWitt equation, he didn't write down the Perez, Einstein-Hamilton-Jacobi equation. What he wrote down is actually not, I think, correctly formulated, because there should be a complex conjugate, but he wrote down the Klein-Gordon inner product, essentially. And we also nicely got the date of the meeting, which fits exactly with DeWitt, not with DeWitt's later recollection, but with DeWitt's contemporaneous grant report, that he was working on this in 1964. So this is the kind of best evidence I think we have that really, at least for DeWitt and for Wheeler at that time, the equation wasn't the important thing. And this in some sense is a response to Bergman, that Bergman may have written down some kind of heuristic H psi equals 0 expression, but he never had anything that could form something like the role of the inner product. And this is what DeWitt writes in his 1967 paper. And as I said, it's not clear that this is strictly an inner product. At least it gives a kind of way of calculating these kind of quantities, and he then applies this to a simple cosmological model, and it's something you can then kind of use to actually calculate inner product like quantities. And so just to conclude, I think the concept of physicist rigor is helpful to understand this case of study. We have a kind of hypothesis that it was actually the inner product that was crucial for Wheeler and DeWitt themselves, but also for the community in general, of understanding that they'd done something that was, to some degree, well-posed or rigorous. It was rigorous enough by the standards of the day, unlike the earlier heuristic expressions that Dirac and Bergman had written. And it's partly, I mean, in addition to the kind of structural power that they had within the American system in excess of the Syracuse school, which is clearly a factor, but I think it's part of the reason why the equation is called the Wheeler-DeWitt equation, is because of the inner product, not the actual functional form. And so I think there's a useful concept of physicist rigor that's kind of tied to groups of local physicists. It's kind of local in space and time, and it's not necessarily really parasitic on the mathematical notion of rigor, and not dependent upon whether there's a kind of later fully rigorous formulation of the problem. And indeed, in this case, there isn't in a substantive sense. Thank you very much.
Yeah, questions?
I think we should take 15 minutes, and because we're the lunch reservations.
Okay,
so
cool.
we've got time for that.
Okay.
Jingy?
Thank you. This is very interesting. So this might be an ill-formed question, but I'm like.
By physicist standards or mathematician standards?
This might be a non-rigorous question. But I'm curious about what you said about physicists writing down some sloppy thing and then someone else coming and fix it up. And I sort of see the first thing not as coming up with something that's going to be verifiable, but sort of as proposing a kind of hypothesis guided by intuitions and how you're embedding the community and see salient features of how things are connected. And later what's going on in the process would be some sort of folks writing down exact conditions under which this particular hypothesis can be either tested or be applied to other things. So I feel like it would be I see the second stage as a kind of integral part of the sort of rigorification.
So I completely agree. I mean, I guess I kind of would want to go back to the beginning of the talk and kind of rework it in the following way, that there's two notions of rigorification, right? There's rigorification up to the standard of mathematicians, and then there's rigorification up to the standards, to some weaker standard. And my kind of claim is that in many areas of theoretical physics, it's really the second one that's doing the heavy lifting. And physicists, I mean, I think it's not all of them, right? But some of them just really do not care whether a mathematician will be happy with the standard of their derivation. What they care about is a slightly weaker set of norms. I guess what justifies that is that in the past, this has been empirically successful as a strategy. And in this particular context, it's slightly odd and different because there's very little empirical evidence. But so I think there is definitely a relationship between the norms of initially whether something's rigorous enough to even understand what it means, and whether people are happy that there's a kind of plausible rigorification process. But my feeling is that in both cases, it's not, the physicists themselves are really aiming for something slightly weaker than mathematicians' rigor. I think in this case, you could understand I think you could understand the inner product problem. They were expecting there to be something that looked closer to an inner product. Whether it could ever be defined, because it's on infinite dimensional space, whether it would ever be like a measure up to the standard of measure theory, an inner product with a well-defined measure up to the standard of rigorous measure theory, I don't think it's necessarily a problem. I think they thought this is close enough to the kind of inner product that we'll be able to make mathematical sense of as physicists. And that's the kind of optimistic interpretation of what they got to, which also didn't pan out.
I might agree with the questions there. I was going to ask a question as well, but I'll be at the back of the queue. It was just on that point, I was kind of wondering, you said a little bit more about what guides the physicist norms, but part of how you talked sounded kind of in the most like anti-realist sense of Kuhnian, that they, just the community just sets up a set of arbitrary norms and then holds by it. But then you said something like norms that have worked well in the past. But do you have more to say about like where these norms come from and how they kind of evolve from place to place or context to context? I
think a lot of the norms in this case are going to come from quantum mechanics, right? And the use of quantum mechanics to do successfully experiment and describe the world. And I guess the point is that physicists, they don't usually typically learn quantum mechanics in a fully mathematically rigorous way, right? So I think a hypothesis would be they want the objects in the theory of quantum gravity to be well defined as the objects in quantum mechanics as they understand quantum mechanics. And there's justification that they're like, well, what's important is that it's cleaned up enough as the theories that we use to do empirically successful work. So that's what I would guess. So I definitely wouldn't. I am an anti-realist in some shades, but I'm an empiricist. So I would take these to be things that are influenced by social context and particular communities. But I think ultimately they're going to be highly constrained and influenced by the use of mathematics to make successful predictions and descriptions of the world.
And your value judgment is that this is good practice? Is there like an implicit ad hominem, not ad hominem, like critique of the ways in which these people practice? They should be holding themselves to higher standards.
No. I actually think to some extent what DeWitt was doing was very well motivated. I think at least at that level, right? I think there's other problems with the Wheeler-DeWitt equation, but I think given the extent to which canonical quantization was a successful route to dealing with lots of other problems. Of course, like one of the problems that I listed is precisely the problem that loop quantum gravity was designed to deal with. I think probably the problem that he underappreciated that wasn't really fully understood at the time was the problem about the symmetry group not being a Lie group. But I think at that time that was probably the right norm of rigor. And like I said, I think ultimately the problem is there's no empirical data to start constraining these things.
James,
I like this this broad picture of thinking about mathematicians as having one set of norms and then maybe physicists have a different set of norms. But I'm kind of I'm struggling to come up with a concrete idea of what the norms might be in theoretical physics that would sort of underrise that notion of rigor. Like, because you focused on the issue with the inner product. Because you could think about that as like very local, as like in order to interpret something as a quantum theory, like the inner product plays a sort of central role in certain like setting up measurement theory and so on. And so like maybe it's a mathematical structure of some kind, but it's not quantum theory.
Sure.
It can't play the kind of representational roles we want.
It seems like a reasonable, like, necessary condition for something to be a quantum theory, right?
But I'm just thinking that's very local and context specific, and you might even.
I mean, the other example that I mentioned, I think, is maybe useful, right? Like, the problem with the operator ordering is it introduces, like, arbitrary quantities, right? So the difference in operator ordering can be measurable. And so that's a kind of very sensible thing to worry about if your formalism is undetermined in ways that, like, introduce numbers that can be arbitrarily specifiable. So I kind of feel like a lot of it is about it's kind of mathematical ambiguities that lead to quantitative ambiguities in the theory rather than maybe formal ambiguities or ill-definedness. That's like, so if you could show that all the ill-definedness will never show up in measurable numbers, I think most theoretical physicists are like, fine. But I think the very fact that it shows up in the theory and you end up having to add in arbitrary quantities is probably what they worry about most. It's a kind of maybe it's an empiricist kind of intuition about it's so unrigorous that there's ways to add in random numbers to it.
Or you get like infinities.
Or you get infinities, right? And I mean, so Dirac really, his principal reason for abandoning this approach was problems with renormalization, regularization, right? And so for him, that really, like, I mean, famously, right, he never thought that quantum field theory was, to understand, like, ever good up to that standard. And so he clearly, although he's this famously, like, in some ways heuristic and sloppy person, cares about some concepts of rigor. And maybe this quantitative idea is the way to frame it.
So, I'm trying to be as concise as possible. So what you say is that kind of, at least the image I got from the presentation is that let's say the notion of rigor from mathematics, let's put it in the sense, it's a straight line. You have a foundation, you know exactly what rigor is, and you know exactly what it is. Whereas for the physicist, it's more like a circular feedback loop. I can be as sloppy as I can. If I get empirical data, then I fix it slightly. I keep fixing it until, as you said, all the kind of like random numbers, random observables that pop up disappear. And that's sufficient. So it's kind of more like a constant feedback loop. And what starts off as the beginning, like what you showed in this case, it doesn't really matter. It can be as rigorous as possible. As long as we get something out of it, then we can fix it as we go along. In theory, you could have found a measure if you had some empirical data.
I think possibly, I'm not sure how close they were to ever getting a useful theory of quantum gravity out of this. I mean, I think what I would like to say, though, is that there's a kind of research tradition level. So I probably want to take the scale of the idea that, like, norms of rigor are kind of within a tradition. I think this fits well with the quantum gravity and the particle physics examples, right? So it's not like there are norms of rigor in particle physics that are very importantly related to the norms of rigor in string theory, for example. So I feel like the problem is often that the initial empirical kind of grist that, like, gets the notion of rigor, like the cyclic process that you're talking about, going, can kind of run out, and the norms of rigor then, like, in some sense, being used by a community without any reference to empirical approach, because they're, like, inherited from past empirically useful context. So I think I like the picture, but I would want to have, like, a little bit of more structure.
Okay, I don't know if it's a well-formed question, but maybe I'm going to reformulate what I understood and then frame it as a question. Is like, okay, in physics and even mathematics, what could be presented as implicit reference to the potential future. Like a testable hypothesis is something like maybe people are going to test, and a conjecture, I mean, people are going to. And you're saying that a notion of rigor in physics cannot be that. Cannot be something that, because what does the heavy lifting is the norms of the community. And so the example with the Wheeler-DeWitt equation, are you saying that basically the thing that mattered here was not was not the equation itself, was the inner product derivation, because that was what's the norms of the time accepted? And so is it like rigor is in a way circumvented in a heuristic process? Like the reference to the potential future is not about rigor itself, but it's about fruitfulness or something, and this is not given by rigor at all.
I think maybe I was trying to make too many slightly different points at the same time. So what I was trying to say is that the mathematicians, the promissory note for the future with regard to the mathematician's notion of rigor, I don't think is important. I think plausibly along the lines that Jingy suggested, there could be a promissory note with regard to theoretical physicists' notion of rigor. And so the idea is that DeWitt's derivation or presentation in a product gave a kind of indication that something that along the lines of a working physicist's way of using quantum mechanics would be achievable in quantum gravity, rather than that quantum gravity would be it would be possible to formulate it as fully rigorous theory, which I don't think that physicists are motivated by. So I think at the time people care about rigor because they want to have things that they can understand, and there might be some indication in the future that it'll be more rigorous. But I don't think what's important is that it will be able to approach mathematical rigor. For most theoretical physicists, that doesn't seem like the kind of problem that such a promissory note isn't something they put that much kind of credit. They don't give much credit or weight to.
Anna, you're done.
It's related to Ram's question in a sense. And I wanted to ask this question to James as well. Really, one thing that I don't really get is what is the motivation for mathematical rigor over and beyond getting, empirical adequacy and fit or empirical prediction?
I think.
Why do you?
I think there is also a heuristic function, right? That having well-defined mathematical objects gives you routes to deforming them, right? And so, it's in virtue of the fact that Hamilton could write classical mechanics in this beautiful algebraic bracket structure that they could turn it into quantum mechanics. So I think physicists, say look at group theory as well, right? In virtue of the fact that you could give these very general group theoretic formulations of physics, there's then a nice way to generalize it. And so I think physicists are pretty interested in precision in mathematics, often because it gives nice heuristics for slightly changing or enlarging structures as well. So I think that's also a motivation.
But is that a generalizable thing, or is it just an exploratory thing? Well, we might get this.
Yeah, exploratory. No, it's a heuristic, right? So there's a heuristic value of rigor, ironically. So yeah, I think that's true. But I do think ultimately what we were talking about earlier, that rigorous enough to not have numbers coming into your calculated quantities is pretty important to physicists, because that's what they really care about, right? Is being able to calculate something that you can then test.
But in the case that James was talking about, the axiomatic growth theory, where you spend all this effort in making these theories really mathematically rigorous, but then you struggle to reconcile them with empirical data, then what is the point of that?
That's what David Wallace and most people would say, right? It's not I guess some virtue of the algebraic approach is heuristic, though, right? People do have use techniques from it.
I was just going to say your point about generalization. That's very present definitely in the earlier days. They were, because the idea in the 50s, basically everyone thought QFT was was not going to be the final theory of relativistic quantum theory. So they were sort of, it really was like an atmosphere of like, something's wrong here. So we want to characterize the theory more carefully in order to understand how we can relax various assumptions that we're like proof to.
Mm-hmm.
So it was.
And the hope would be that theory would be testable.
Yeah, it was understood in that context of like theory building, as a tool, as a indirect tool for theory building, for future theory building. But then obviously the fate of QFT, like it becomes in the 70s, everyone is suddenly like, oh, actually maybe QFT is an okay theory, and then I think that probably changes the aims of these communities and the way that they start talking about rigor as well, potentially.
So is the idea that if you fix the maths, then you might get the extra empirical structure that you believe that would be there if the theory is not complete?
That you might be able to
explain or predict.
You might be able to, because nobody had a theory of nuclear interactions, so that's what they were trying to get. Like there was a problem with empirical adequacy. Quantum field theory wasn't empirically adequate at the time, but after QCD comes along, like the situation changes.
Is this the time which meant to go to lunch?
We've got a booking at 12:30, so we still have a little bit of time, but we should.
Jingy had a finger.
Well, I have a very small finger.
I also had a very small finger.
To end this question, which is like, I also think, at least in the causal alternative theory case, like James said that the motivation might not be very philosophical, but to me it is quite philosophical, which is here's a technique that works in reality, but we are not sure why it works, and doing this kind of mathematization of the exact conditions under which this works and exactly why we can like discard the high energy single distribution.
It's not similar to calculus, right? Right. So I mean, wanting to know why calculus works seemed like a really important project for like whatever, how many 100 years it took, right?
Yeah. So like just to give a story about exactly why we are allowed to do the things that we do in practice.
Explanatory.
Explanatory.
So there is explanatory.
Yeah, before the axiomatic QFT situation, it's a lot less clear.
But I think we should be very careful not to fetishize mathematical rigor. Because there are clearly grades of rigor even within mathematics. And so if you read the philosophy of maths literature, a lot of people are kind of saying, like, you can't logicize mathematical proofs. You can't make these perfectly rigorous in some logical standard. And so I think there are grades all the way down from mathematics through physics into philosophy. And then philosophy there might be a kind of horseshoe or something.
And then from philosophy into metaphysics.
No, well, so metaphysics, they try a certain kind of rigor. And it's interesting to try and think about applying the kind of standards of mathematical rigor. But I'll talk a bit more about this. Mark Wilson is the invitation.
Let me just, there's another interesting example where people didn't care that much, right? Like, it's not that physicists cared about the mathematical pathologies of Newtonian mechanics and thought that it was absolutely had to resolve collision singularities and redshift continuity problems in 19th century Newtonian mechanics, right? It's just the theory wasn't seen as problematic that there were these mathematical issues with its formulation. It was seen as an incredible successful theory, right? So there's definitely some aspects of rigor that, like, for a very, very empirically successful theory that can be formulated, like, very clearly, the fact that there are some, like, parts of the theory where the math starts looking a bit chonky doesn't seem to be important to many physicists, right? I mean, it's similar with singularities, that it was only once they started having models that looked physically realistic that showed singularity that this started being a problem in general relativity. And we wouldn't usually think about it as a rigor problem in this case, right? We think about it as a physical problem of general relativity. So I mean, maybe it's an interesting example. I know Karim and Nahara wrote about it, to compare the way that singularities are understood in quantum field theory as opposed to GR, right? But it doesn't seem like one would say that. I'd be interested in anyone's ever said this. The existence of singularities in GR shows the theory isn't rigorously formulated. That seems like the wrong thing to say, right?
I'm not sure.
Would you think?
I think like instantaneous gravitational effects in Newtonian gravity can be seen as a problem of rigour, and it's a problem of rigour that people didn't really know how to address for a long time. But the description, the critique of it as like occult forces is kind of saying, you haven't formulated your theory properly.
But not mathematical rigour, right?
I don't know.
Yeah, that's interesting.
Anyway, it's just the time to.
Yeah, should we stop there?
Yeah.
Thanks for hearing.